Welcome. This is COM4D, Inferring Compositional 4D Scenes Without Ever Seeing One, a CVPR 2026 paper from Insight, Sophia University. Think about how we perceive the world. At any given moment, a scene around us contains multiple objects, some static, like furniture, and some dynamic, like a person or an animal moving through it. The whole scene evolves in both space and time. That's what we mean by 4D. COM4D is a method that, given a single monocular video, reconstructs the complete 4D structure of such a scene. It jointly recovers the geometry of every static and dynamic object, their spatial arrangement, and how that arrangement changes over time, all without relying on any category-specific priors, and crucially, without ever having been trained on compositional 4D data. So why does this matter? Scene-level object decomposition has seen impressive progress, but almost entirely in the static 3D setting. Methods like PartCrafter, MIDI 3D, and SceneGen can reconstruct multiple objects from a single image as separate 3D meshes. That's genuinely useful, but the moment something in the scene starts moving, these approaches have no answer. On the 4D side, methods like StarTrack, C4D, and Shape of Motion can track and reconstruct structure over time, but they treat the scene as a whole without decomposing individual objects. More importantly, they were never trained to reason about the parts of an object that are currently occluded. So when an object moves behind another or changes viewpoint significantly, the reconstruction breaks down. There is no persistent, object-level 4D understanding. Here's the core difficulty. Compositional 4D data simply doesn't exist at scale. Capturing multiple dynamic objects simultaneously with ground truth 4D annotation requires controlled multi-camera rigs, motion capture systems, or carefully simulated environments. It's prohibitively expensive. What we do have is plenty of static multi-object 3D scenes and plenty of single-object 4D animations. COM4D is built entirely around this constraint. Our solution starts from a key insight. We already have powerful pre-trained single-object 3D generators. Instead of building from scratch, we extend one, teaching it two new capabilities on top of its existing priors. Attention parsing is our training strategy. The model learns both spatial attention, connecting objects within a single moment, and temporal attention, connecting the same object across frames in disentangled transformer blocks, so neither interferes with the other. Then at inference, attention mixing activates both simultaneously. Static and dynamic objects jointly attend across both space and time, giving us the full compositional 4D picture. So how do we train? We take a single diffusion transformer and teach it two things separately. When training on static scenes from 3D front, the even-index transformer blocks perform multi-instance attention, learning how objects relate spatially to one another. When training on single-object animations from deforming things 4D, the odd-indexed blocks perform multi-frame attention, learning how an object deforms over time. The other blocks default to local self-attention in each case. We call this attention parsing. One model, shared weights, two complementary capabilities, learned from data that's actually available. At inference, we give the model something it has never seen before, a video with both static and dynamic objects together. The model was never trained on this type of input. So how does it work? The answer is diffusion forcing. Each object latent is assigned an independent noise level during training, so the model learns to handle tokens at different stages of denoising simultaneously. At inference, once a frame is denoised, it becomes clean context for the next one. Static objects act as stable anchors, and the dynamic object generates frame by frame, always conditioned on its history and the grounded static scene. But wait, why can't we just run static reconstruction and 4D reconstruction separately and place the results in the same space? The answer is that without mixing, there is no shared spatial grounding. The spatial blocks and temporal blocks never see each other's outputs. The model has no way to know where the dynamic object should be relative to the static ones, or at what scale. In practice, without mixing, the generation simply cannot figure out placements and relative scales of objects. Things end up floating in inconsistent positions. Mixing is what forces every object, static and dynamic, to be jointly reasoned about at every time step, so the final 4D scene is spatially coherent. Here we show additional results. We also show additional static 3D compositional results compared to PartCrafter and MIDI. These are additional 4D object results, showing different views of generated dynamic objects. In quantitative comparisons on 3D scenes, our method significantly outperforms others in CD and F-score for 3D front and 3D front occluded datasets, achieving better reconstruction accuracy. For 4D objects, our results also show state-of-the-art performance on the Deforming Things 4D and Objaverse datasets across most metrics, demonstrating high fidelity and improved completeness. Thank you for watching this video. Please visit our website for more information on our work.